Welcome to LLMs Research Podcast.
Hello.
Today, we are taking a serious look at, one of the most explosive areas in artificial intelligence. We are talking about the massive leap in context windows.
It really is an evolution that has happened at just breakneck speed.
Exactly. This deep dive is about that journey, how we went from models that could essentially only remember a single page of text, about 512 tokens, to the monsters we see today.
Right. Models that can process millions of tokens.
We're talking about feeding entire libraries into a model at once.
It's the difference between reading a pamphlet and reading, the entire works of Shakespeare, plus a history of the Roman Empire, all in one go, and remembering every detail.
So our mission today is to unpack the engineering breakthroughs that made this possible, because it wasn't just make the computer bigger, was it?
Not at all.
We're going to look at the hardware tricks, the math hacks, and the entirely new architectures that smash what we call the memory ceiling of AI.
Right. And to appreciate where we are, we have to look at where we started. The seminal paper, Attention is All You Need. It gave us the transformer architecture. It changed everything.
But it came with a heavy cost.
It did. That standard context window of just 512 tokens.
512 tokens, that's barely an abstract for a research paper. Why was it so hard to just add more?
And that brings us to the villain of our story, the bottleneck. It all comes down to the quadratic complexity of the self-attention mechanism.
Okay, let's unpack this. Quadratic complexity.
That sounds painful.
It is. In computer science terms, we call it O of n squared. And what that means in practice is, well, every time you add a token to the sequence, the model has to compare that new token to every other token that came before it.
So it's checking the relationship between every single word pair?
Exactly.
So if I double the length of the text I give the model, the work doesn't just double?
No. If you double the length, the memory and computational requirements, they quadruple.
Wow.
If you triple it, it goes up by a factor of 9. You can see how quickly that just explodes. You hit a hardware wall almost immediately. It's like being at a dinner party. If there are 4 people, introducing everyone is easy. If there are 1,000 and everyone has to shake hands with everyone else,
you're going to be shaking hands forever. That was the state of affairs for a while. The barrier preventing us from feeding books into an AI was this math problem.
So naturally, the first instinct wasn't to solve the math perfectly, but to, what, approximate it?
To cheat. Phase 1, the era of sparse attention.
Right.
Researchers looked at that O of n squared matrix and asked, do we really need every token to attend to every other token?
Logically, probably not. Does the word "the" on page 1 really need a deep semantic connection to the word "apple" on page 50?
Exactly. So papers like Generating Long Sequences with Sparse Transformers at Big Bird introduced this idea of sparse attention.
So instead of a full grid, the model only attends to a subset of the sequence.
A subset, yes. And that drastically reduces the workload. It brought complexity down to something closer to linear, or O of n times the square root of n.
And then longformer came along.
Which was a clever hybrid. It used a sliding window for local context, so the words immediately around you, and combined that with task-motivated global attention.
So it's like reading with a flashlight that only illuminates the paragraph you're on, but you've also marked a few key landmark chapters in the distance.
Precisely. And while these were clever engineering workarounds, we have to be honest, they were approximations.
You're losing something.
You are. You're trading a bit of accuracy for length. You aren't getting the full, dense attention matrix. You're betting that the skipped connections weren't important.
And in deep learning, betting against data usually isn't a great long-term strategy.
Right.
We needed a way to get the full picture, the exact attention, but without that explosion in cost. And that brings us to phase 2. This is where the story shifts from math approximations to hardware intelligence.
The Flash era. And this is arguably the most critical pivot point in modern LLM scaling. The breakthrough was FlashAttention.
Now, most people assume FlashAttention is just a faster algorithm. But reading the paper, it seems like the authors realized the bottleneck wasn't actually the computation, it was memory.
Exactly. Memory bandwidth. They identified an I/O awareness problem.
Okay, what does that mean?
To understand this, you have to look at GPU architecture. You have high bandwidth memory, or HBM, which is massive, but relatively slow to access.
And then on the chip itself.
You have SRAM, which is tiny. We're talking megabytes, but blazing fast.
So the HBM is the big library, and the SRAM is your personal desk where you do the actual work.
That's a great way to put it. Think of the GPU like a master chef. The calculation, the math, is the actual chopping and cooking. That happens in the fast RAM on the cutting board.
But the ingredients live in the pantry, the HBM.
And the pantry's down the hall. Before FlashAttention, the standard attention implementation had the chef running to the pantry, grabbing one onion, running back, chopping it, running back to the pantry for a carrot.
So the GPU compute cores spent 90% of their time just walking, not actually cooking.
Precisely. The authors of FlashAttention said, let's stop making the GPU wait. They reorganized the computation using a technique called tiling.
Tiling.
Essentially, they bring a whole basket of ingredients to the counter at once, do all the chopping and mixing in the fast RAM, and only write the final dish back to the pantry.
That's the genius of it. They didn't change the recipe. The math is exactly the same as standard attention. They just optimized the kitchen logistics.
And the gains were massive. We're talking linear scaling with exact attention. And it evolved rapidly. FlashAttention 2 came along and optimized the parallelism to keep the GPU even busier.
And now we're at FlashAttention 3, which seems tailor-made for the Hopper architecture, like the H100s everyone is fighting over.
It is. FlashAttention 3 leans heavily into asynchronous execution. It allows the GPU to overlap that data transfer with the computation even more effectively.
I saw a stat that it reaches up to 1.2 PFLOPS on an H100. I mean, that is staggeringly fast.
It is. And this hardware-software symbiosis is what effectively enabled the training and serving of models with contexts of 128,000 tokens and beyond. The hardware wall was smashed.
But solving one bottleneck just reveals the next one.
Always.
Once you have a window that spans 100,000 words, how does the model know where things are? You know, if I give you a novel, chapter 1 is at the start and chapter 10 is at the end. To a model, that's just a stream of numbers.
This is phase 3, encoding position. In the old days, we just, added a number to the token embedding, token 1, token 2, token 3.
Absolute positioning.
Right. But absolute positioning generalizes terribly. If you train on 2,000 tokens and then try to test on 2001, the model freaks out because it has never seen the position ID 2001.
So we needed a system that cares about relative distance, not absolute coordinates.
Enter ROPE, or Rotary Position Embedding. This was introduced in the Reformer paper, and it effectively took over the world. It's in Llama, Mistral, Palm.
Why did ROPE win? What was so special about it?
Yeah. It's a kind of mathematical elegance. Instead of adding a number, ROPE rotates the embedding vector in geometric space.
Yeah.
The angle of rotation corresponds to the position.
Okay.
And the magic is that when you compare two tokens, the absolute positions cancel out, leaving only the relative distance between them.
So the model knows word A is 50 words away from word B, and it doesn't matter if that happens at the start of the book or on page 500.
Exactly. It decouples the relationship from the absolute position. But ROPE wasn't the only contender. We have to mention ALiBi attention with linear biases.
ALiBi is fascinating because it seems almost too simple. It just penalizes attention based on distance, right?
It does. Think of it as a spotlight that naturally dims the further away you look. If a token is far away, the model just pays less attention to it by default.
Unless the content is super relevant.
Right. And the killer feature of ALiBi was extrapolation. Because that logic dimming over distance is consistent, you can train on short sequences, and the model can handle longer ones it has never seen before. It doesn't crash when it goes off the map. It just keeps applying the penalty.
Yeah. So we have the hardware with FlashAttention and the positioning with ROPE or ALiBi. But here's the scenario everyone is dealing with right now. You have a model pre-trained on, say, 4,000 tokens. You don't have millions of dollars to retrain it from scratch, but you need it to handle a 200-page contract.
This brings us to phase 4, the stretch, or, more technically, interpolation strategies.
This is where we get into the rubber band problem.
That's a great way to visualize it. The first attempt was position interpolation, or PI. Imagine you have a ruler with markings from 0 to 100.
Right.
You want to measure up to 200, but you can't make the ruler longer. So you just squash the numbers. You relabel the ticks so 0 to 200 fits on the same stick.
But if you take a rubber band with text written on it and stretch it to double the length, the letters get distorted and blurry.
Exactly. The resolution drops. In single processing terms, you lose the high-frequency information. The model gets blurry vision.
So it might get the gist, but it loses the sharp detail.
The specific, precise relationships between nearby words get lost. So PI gave us length, but it killed the fine details.
So how did researchers sharpen the image back up?
They moved to NTK-aware interpolation. Without getting too deep into the neural tangent kernel math, think of this as a smarter stretch. It knows that high-frequency features, the fine details, shouldn't be stretched as much as low-frequency features, the general themes.
So it preserves the sharpness of the text while extending the canvas.
Right. And this iterative improvement continued. We got Yarn, which is yet another LongRoPE extension.
Great name.
Right. It combined NTK interpolation with temperature scaling, essentially tweaking the focus knob of the attention weights.
And this path eventually led to LongRoPE, which feels like the current state of the art for this technique.
LongRoPE is impressive because it uses an evolutionary search algorithm to find the optimal scaling factors. It doesn't just stretch everything uniformly. It finds a non-uniform way to resize the positional embeddings so you can hit 2 million tokens.
Without making the model stupid at short context tasks.
That's the key.
Mm-hmm.
Usually when you stretch a model, performance on short questions gets worse. LongRoPE managed to keep the short game strong while unlocking the long game.
But again, we are still talking about fitting things onto a single GPU or a standard cluster. What if 2 million isn't enough? What if we want 10 million or infinite?
Now we're in phase 5, system-level scaling.
Yeah.
Because at a certain point, a single GPU, no matter how optimized, just runs out of memory.
So we move from algorithm design to distributed systems design.
And the headliner here is ring attention.
The name gives it away a bit.
It does. Imagine you have a sequence so long it doesn't fit on one chip.
Hmm.
Ring attention chops that sequence into blocks and distributes them across a circle of GPUs.
Like a bucket brigade at a fire.
Exactly. GPU 1 computes its part of the attention, then passes its key value block to GPU 2 while receiving a block from the previous GPU. They overlap this communication with the computation.
So while the chef is chopping, the assistant is handing them the next basket of ingredients in a continuous loop?
It allows near infinite context, limited only by the number of GPUs you can chain together. And there's a variant, striped attention, which is optimized for the triangular shape of causal attention.
Because models like GPT only look backward, so half the work is redundant.
Correct. It avoids wasting time on the empty parts of the matrix while doing this ring pass.
Now, everything we've discussed so far assumes we are sticking with the transformer architecture. We're patching the holes in the boat.
We are.
But there is a growing group of researchers saying, maybe we need a different boat.
This is the frontier beyond the transformer. We have to talk about Mamba and RWKV.
These are exciting because they attack the root cause, the key value cache.
Right. In a transformer, during inference, you have to store the history of every token you've generated to calculate the next one. That cache just grows and grows. It eats memory.
And Mamba doesn't do that.
No. Mamba is based on state space models, or SSMs. It compresses the history into a fixed-size state.
So it doesn't need to look back at a 10 million token history file.
It doesn't. The state captures the relevant information as it goes. It's effectively linear scaling. It doesn't get slower or more expensive the longer the conversation goes.
And RWKV is aiming for a similar sweet spot.
RWKV is a fascinating hybrid. It's designed to be trained like a transformer, so it can use all our massive parallel hardware, but run like an RNN during inference.
Constant memory usage, infinite context potential.
That's the promise.
Okay. So we have the tools. We have the 10 million token windows. The engineering victory is undeniable. But I want to pause the celebration and ask the hard question.
The so what question.
Exactly. We're seeing marketing claims of 1 million, 2 million tokens, Gemini 1.5 Pro, Claude 3. But just because I can read a library doesn't mean I can synthesize it. Are these models actually smart at that scale?
This is the reality check. And frankly, it's the most important part of this discussion for anyone actually using these tools. We are facing an evaluation crisis.
The standard benchmark for a long time was needle in a haystack, right?
Right. You hide a random passphrase in the middle of a massive document and ask the model to find it.
And honestly, that test is broken now.
It's too easy. Most top-tier models score 99% or 100% on it.
Because it's just retrieval. It's Streeterall plus F on steroids.
Exactly. Finding a password isn't reasoning. The new benchmarks, like Ruler and LongBench v2, are exposing the cracks. They ask the model to do things like variable tracking or multi-hop reasoning.
Like, find the clue on page 5, connect it to the contradiction on page 5,000, and then explain the mode on page 10,000.
And that is where models start to fall apart. The research shows that effective reasoning often degrades as the context length increases. The model gets distracted by the sheer volume of irrelevant information.
So we've built a librarian that can hold 10 million books, but maybe can't understand the plot connection between book 1 and book 100.
That's the perfect analogy. We have solved the capacity problem, the hard drive problem, but we haven't necessarily solved the attention span or the cognitive span problem.
It seems like the next frontier isn't just more tokens, but better attention.
I think that's right. The focus is shifting from how much can we fit to how well can we use what we fit.
So to recap the journey, we started at 512 tokens, blocked by quadratic math. We broke through with FlashAttention optimizing the GPU. We figured out positioning with LongRoPE. We stretched models with interpolation. And now we're chaining GPUs with ring attention, or even abandoning the transformer entirely.
It's been a massive engineering sprint.
Which leaves us with a final provocative thought. We've spent years trying to give AI photographic memory. But if a model can read 10 million tokens and still struggles to reason across them, have we essentially created a super reader that doesn't understand what it's reading?
It raises the question, is context length actually a proxy for intelligence, or have we just built a really, really big buffer?
A fascinating place to leave it. Thank you for diving in with us. And remember, if you want more interesting podcast episodes and weekly research papers analysis, then please subscribe LLM's Research Podcast for free.
See you next time.